Okay, Engineer Amri, we can start now.
Okay. Assalamu alaikum wa rahmatullahi wa barakatuh. Good evening, everyone. So this is our second lecture of the 4x4 drilling fluid training. I'm Amr Ibrahim. I already introduced myself yesterday, so we need to reintroduction. So this is our training agenda that we talk about. We finished day number 1, drilling fluid functions, and today we are going to talk about day number 2, which is it's all about pressure plus the rig hydraulics. And tomorrow, inshallah, will be the mud engineer or mud cooker, and this will be a very interesting lecture. And day number 4, it will be some of the two of the most common problems related to drilling fluid while drilling, which are the loss circulation and stuck pipe. So day number 1, okay. So today we will talk about day number 2. It's all about pressure and hydraulics. So when we talked yesterday, we talked about the functions of the drilling fluid, and we started with number 1 and the most important function, which is the pressure control. You remember when we talked, the pressure control is the most important one. Why? Because if we lost the pressure control, maybe we have a kick, maybe we have a blowout, we will lose personnel, we will lose equipment, and we will lose everything. So pressure control, it's be or not to be. So you remember this model from yesterday that we need to have our hydrostatic pressure, the pressure that is we got from the mud column width and the depth. This hydrostatic pressure should be greater than the formation pressure and bigger than the fracture pressure. Less than the fracture pressure, sorry. The hydrostatic pressure should be greater than the formation pressure and should less than the fracture pressure. So we have something called the trip margin. Someone asked me about it yesterday. When we drilling, say for example, we have 3000 psi formation pressure. So what will be our hydrostatic pressure? Our hydrostatic pressure should be higher than the formation pressure with the trip margin, over balance between 100 to 200 psi, which is the trip margin. And we can increase this value, but we are caring about this value because there is another value it will be added while drilling, while circulation, which is the ECD. We will talk about in a minute. So we keep the overbalance in the hydrostatic condition 100 to 200 psi. 100 to 200 psi. This is the trip margin. And here the drilling mud achieves this by providing hydrostatic pressure just greater than the formation pressure. If we have a large window, we don't want to be at the middle way. For example, if we have formation pressure of 3000 psi and we have fracture pressure of 4000 psi, it is not necessary to have a hydrostatic pressure at the middle way, 3500. This is not a good practice. We just want to control the formation, that's it. Just use 100 or 200 psi as a trip margin and consider the ECD, which is the increase of the mud weight or the circulating mud weight while circulation. So you should take care about this. So you just need the formation, the hydrostatic pressure to be just greater than the formation pressure. I think you remember this from yesterday. This is the equation of how to calculate the hydrostatic pressure. And I told you this is the most important and the most common equation of the oil field at all. Because this is calculates the hydrostatic pressure. The constant multiplied by the mud weight, whatever the unit, multiplied by the true vertical depth, meter or feet. And I told you the third one is the most common one, 0.052 multiplied by the mud weight, ppg multiplied by the depth. So today we will add about this, the ECD, and we will talk about the pore pressure and the fraction pressure in more detail. So the ECD, if we go back to this slide, our mud come from the surface, come from the mud pump to the surface lines, through the drill string, get out from the pit, and go to the annulus. At this process, and this is the second part of today's lecture, we will talk in details about the rig hydraulics. All this way, there is a pressure loss or pressure reduction due to the friction in every part. When we are talking about the ECD, the part that is necessary now is the friction of the pressure reduction in the annulus. The pressure reduction in the annulus. Where this pressure go? You know for sure that the energy or the power, it will not go anywhere. It will not vanish. So this pressure loss, which is lost from the mud itself to the formation, where it will go? It will apply to the bottom hole pressure. So if we have a pressure gauge in this area and we want to measure the mud weight or the pressure at this area, we will find that the pressure is equal to the hydrostatic pressure of the mud column from the surface to the point that we are measuring at the bottom hole, plus the effect of the annular pressure loss. Sorry. So we have a pressure increase transferred from the pressure loss of the mud to the annulus, and this pressure loss affects the bottom hole. So if we put here a pressure gauge, we will sense extra pressure. This extra pressure is expressed by the equivalent circulating density. That we have density higher than the actual mud density while the circulation process. And this ECD, how we can calculate it? We calculate it by the density, the original density of the mud, plus the density come from the annular pressure loss. This is the equation. The pressure equals the depth multiplied by the density multiplied by the constant. So if we want to get the density, we will divide the annular pressure loss over the depth multiplied by the constant. And here we go, we can get the additional mud weight or additional density due to the annular pressure loss. And this will be added to our original density to give us the ECD. And the ECD is very important while drilling. You remember yesterday when we talked about the function of drilling fluid, and one of the function is to provide information from the downhole tools. One of these tools is the BWD, which is the pressure while drilling. And this tool is mainly concerned about calculating the pressure while drilling and ECD. And the calculation of ECD is very important while drilling, because sometimes we may drill with narrow window. Narrow window, that is the formation pressure and the fracture pressure are very close. So we have to optimize our ECD. You know that our company, my company now, Schlumberger, or even Halliburton, or any company, are investing a lot of money and a lot of resources to produce fluids that is providing less ECD, just to have, you know, to avoid the problem of ECD while drilling. This fluid is called the high performance mud, especially when you have a very long section, a lateral section, and you have a problem of ECD, it will be a very serious problem for you. So the ECD, you cannot neglect it. Maybe you are drilling, maybe you want to produce very good hole cleaning. Okay, go increase the viscosity. Hey, stop. If you increase the viscosity too much, you will have too much friction. You will produce too much ECD. This is not the good way. Okay, so we can increase the angular velocity. Okay, again, you will have a high ECD. Okay, I will increase the RV and dilute the annulus with cutting. Hey man, you will increase the ECD again. So all the time you are thinking about the ECD, because your mud weight, you can control it. You can increase or reduce the mud weight from the service. It's okay. But the ECD is a factor of a lot of factors. It's affected by a lot of factors. The cutting load in the annulus, the density of your mud, the design of your BHA, all of this affects the ECD. So the ECD is a serious problem. And if any one of you read about the new technology, which is the BWD, the MBD, the managed pressure drilling, we are drilling with very narrow window. We are trying to avoid the ECD. So the ECD is a big issue and a serious problem. Okay, so now we will start talking about the two pressure that we cannot control: the formation pressure and the fracture pressure. The formation pressure is the pressure of the formation. It is a characteristic of the formation. We cannot change it. We just play around it. So we have normal pressure gradient. I told you yesterday, most of the formation that we have today is sedimented in a marine environment. And through the millions of years and through the sedimentation, so we have a depth of a formation. Say, for example, 10,000 feet, 15,000 feet, and so on. We have something called the normal pressure gradient. How we calculated it? It's calculated by exploration wells all over the world. There is a study describing how we could calculate this normal pressure gradient. The normal pressure gradient is the expected increase in pore pressure as you go deeper. It is 0.465 psi per foot. It is actually a range 0.433 to 0.465. But this one is the most common, 0.465. So you can tell yourself that If you are drilling in a 10 or 1,000 feet, so you expect to have 465 psi. This is your normal pressure. This is your normal formation pressure or pore pressure. Okay. Let's concentrate in this one because this is very important slide. So please pay more attention with me. I talked to you yesterday that this pore pressure is the result of the overburden pressure, the weight of the column of the rocks, plus the trap pressure inside this fluid. I told you that these rocks have fluid and there is trapped pressure inside. So if you want to calculate the pore pressure, we want to calculate the overburden pressure and the pressure inside the fluid. Okay. So try to imagine in this one, this first one. This will explain to you the effect of the overpressure and the effect of the normal pore pressure. Say we have this spring which simulates the rock grains, okay, and we have this pore fluid. This is a fluid inside the rocks, okay. So if we increase the overburden, and we are not letting the fluid to go out, the drainage path here is closed. We increase the overburden and there is no exit for the fluid. The fluid which is trapped inside the rocks are not flushed out. So what will be the consequences of this? We will have abnormal pressure, right? So this is our normal pressure gradient. If we increase the overburden, but there is no way the fluid inside the formation go out, so the pore pressure will increase. So we will have abnormal pressure. Second case, what if we have extra overburden, but the fluid inside the rocks are free to go? So our pore pressure will remain the same. It is that clear to you? Because we cannot continue until this is clear to you. Because if we want to understand this one, we have to understand this one first. So again, this is our pore fluid and this is our rock grain simulation. This is the normal pore pressure. We increase the overburden. We are not letting the fluid to go out, no flushing. No fluid will go out. So the pore pressure will increase. We will have abnormal pressure. But in the most cases, when we have overburden and the fluid inside the grains flushed out, so our pore pressure will not increase. It will stay constant. Is that clear to you? Please, I need an answer. In the chat or in the voice, it's okay. Is that clear to you?
It's understood.
Okay, very nice. So, please, I want everyone to have your mobile or a calculator with you for the next slide. It's very simple calculation, but just calculate with me. Okay, we talk about the normal pressure gradient is 0.465. So please calculate 0.465 multiplied by 4,000 feet. We are drilling a formation at 4,000 feet, and we want to know the pore pressure of this formation. So how much it will be? If you calculate it, it will be 1860 psi. So if we are drilling a normal formation like most of the formation around the world at 4,000 feet, so we will have 1860 psi. This is the normal bore pressure. Try to focus what we are talking about. We are talking about the bore pressure. This is out of our hand. We cannot control. We just calculate and play with it. So you remember this case when we increase the overburden, but the fluid is not allowed to go out. What is the application of this in the real world? In the real world, there is a concept called a sand lens. It is a sand formation trapped by a shale formation. And the shale formation is impermeable. The permeability is not high enough. So this sand lens, it is entrapped. The fluid inside it, it will be trapped. So if we increase the overburden, the fluid will not go anywhere. The fluid will not go anywhere. And its pressure will be high. So try to imagine this one at 4,000 feet. We are drilling it normally. We expect the bore pressure to be 1860 psi. So if we, for example, we drill it with 2,000 psi hydrostatic pressure, it will be fine, right? So what if we found this sand lens at 2,500 feet? Calculate it with me. If you calculate 2,500 feet multiplied by 0.465, it will give you 1160 psi. So if you are drilling and you expect that everything is normal, so you expect to have 1160 psi at this depth, but you will be surprised that you will have a pressure of 1860 psi. Why? This is the main point why we are talking about the pore pressure in this slide or in this presentation. This is the abnormal pressure that you found a formation which is almost, or most cases, sand lens entrapped with shale formation. You will find its pressure higher than expected. And maybe you have a shallow gas kick, or maybe you have a kick and you close your well and increase the mud well and so on. So this is a serious problem. When you are drilling at a shallow depth and you are expecting that you have, say for example, at this depth, you will drill with, say, 1,300 psi. So you will have a 500 psi difference. You will have a kick because this formation, sand lens formation, contain high pressure, abnormal pressure, and you will find yourself have a kick. The subnormal pressure in this case, if you calculate with me the 5,000 feet multiplied by the normal pressure gradient, this pressure should be 20, 23rd 100, 25 psi, 2300, 25 psi. But when you drill it, its pressure is 1800, the pore pressure. So you have here subnormal pressure. Why subnormal pressure? Again, because of the sand lens, which contain trapped pressure, and its depth is high enough that you have a less pressure that you will expect. Maybe at this time you frack this sand lens and you have a losses. So this is the point of the abnormal pressure and subnormal pressure. This is not the only reason of abnormal and subnormal, but I choose this one to talk about because it is very common and you will hear a lot about it, and it is related to a repeated issue while drilling. So is it clear? I want to clarify to make sure that it's clear to you, because this is very concept. You go out from this training with it, because understanding the pressures, it makes you a better engineer. So is it clear to you?
The abnormal pressure is easy to understand, but for the pressure that is reading less than it should be, the one on the most right hand, was harder to explain, like why that sand lens is not receiving the weight of the rock above it, which is, we know here is 5,000 feet. So if there is nothing protecting this sand lens, then all the weight of the rock above it should apply 2325 psi. So why is it kept low?
As I told you from this one, it's the point that there is no exit of the fluid. There is no exit of the fluid. So the pressure, the pore pressure itself will increase. You know, maybe in the calculation, it's a big difference. But as you said, the effect of overburden may get this number close to the pressure at this point. But I kept the number like this just to explain the point of the trapped pressure. And as I told you, this is not the only reason for abnormal and subnormal. And the project or the reasons of subnormal pressure are more than this. The shell density, a lot of factors. But just this one, I'm trying to explain the effect of the sand lens, the enclosed sand lens, the preventive fluid from going out that cannot communicate with the surface, and the pressure, it changes, you know. So as you said, there is more illustration in this point, but I'm trying to keep it simple to avoid enlarging the time of the session. So it's clear to you?
Not quite sure, but you can move on.
Okay, so I will have some minutes with you. Maybe after the session, we discuss more about it, okay? Or at the end of the session. Okay, Mohsen, but in case how or when drilling, we should always have, as I told you, Alberto, we are using hydrostatic pressure just greater than the formation pressure. It's normal to have 100 to 200 psi margin. Maybe we have more, if we want to increase the mud weight just to avoid the caved shell, to maintain inhibition for the shell. So maybe we increase the mud weight if we have caved shell on shaker as we see yesterday. So, but this is a normal, yeah, 100, 200 PSI. Marcin is asking, but in the case, how we will design or how we will know the hydrostatic pressure? What do you mean HSCP?
Hello, sir.
What do you mean HSCP, hydrostatic pressure?
Yes, yes, I mean hydrostatic pressure.
Yes. Hello.
Because,
Okay, so this is normally when we drilling exploration wells, we are trying to design our well for the normal case, but we are expecting from the geologic surveys that maybe we have sand lens here, so we try to expect what we are facing. And for sure, for the surface section, we install the diverter. Maybe we got shallow gas, and if we got this, we will increase the mud weight depending on what we have. But we will start with the normal pressure, and this is usually done on the exploration well. But in the development well or appraisal well, so you have what you are doing, and you will not concern more about the sand length and over abnormal pressure. Abnormal pressure in case the fluid supported instead of matrix supported. Yes, but also there is a situation that you have abnormal pressure in the matrix supported. But it's not the scope of our session. But yeah, we have both of them, not only the fluid supported. Okay, so the last thing we will talk about it's all about pressure is the formation fracture, pressure. You know, you have three types of pressures affected your rock: the vertical stress, the minimum horizontal stress, and the maximum horizontal stress. You know, this is geologic more than our scope of drilling fluid, but just to know that your rock is affected by a lot of stresses: vertical stress, minimum horizontal stress, maximum horizontal stress. And just a quick info: when we are making hydraulic fracture job, we should study well the propagation of the fracture based on the minimum horizontal stress and the maximum horizontal stress. So we just care about, we have a stress to the formation, and this stress is applied by the hydrostatic pressure, our hydrostatic pressure. And if we reach the point that we will crack the formation, so the formation will be cracked and we will lose the mud and lose the hydrostatic head. And you know, there is some test we are doing for the exploration well. We are doing something called the leak-off test, the LOT, and this is, you start closing your well and you pump quarter barrel by quarter barrel until you see a pressure reduction or pressure leak, and this is your frac point or fracture pressure. And in the development well, you just make something called FIT, which is the formation integrity test, just to test that your hydrostatic pressure will not cause any problem to this formation. So the fracture pressure, it's a big topic to cover, but just try to remember that your rock is expressed to a lot of stresses, vertical stress, horizontal stress, minimum and the maximum, and you are trying to avoid fracturing the formation by knowing its fracture formation by the LOT if you are in exploration well, or performing the FIT if you are in the development well, and you just want to test that your mud is good to drill this formation. Okay, and this is conclusion for our first part of today's lecture, and we will continue in the practical rig hydrology. I can take one or two questions if you have.
Yeah, I have a question about the FIT. So you actually designed the mud weight, and you wanted to test if it's okay to use this mud weight for the well. So what exactly are you measuring during the FIT? Because on the LOT, you basically keep adding the pressure until the formation frac. So you'll see on the pressure versus time plot. But what are you reading or measuring during FIT?
Okay, very good question. The LOT, as we discussed, we continue pumping very slow, very low volume, quarter barrel, until we see the chart of the pressure start to decline, and this is the point that we know the formation is cracked, and this is our fracture pressure. But for example, if we are drilling with like 12 BVG, and we know from the exploration that this area, the fracture pressure is 14 BVG. So just when we start drilling a new section, the weakest point of the section, it will be around the casing shoe of the last section. So we just drill 10 feet or 15 feet and applying a service pressure equivalent to 12 BPG. We calculate the mud weight, the current mud weight in the well for, say, for example, 10 BPG, and we apply the extra pressure equivalent to the 12 BPG applied to the service, and see on the chart the pressure will hold or there is a problem for pressure reduction. If it is hold for 15 minutes and then 30 minutes, most of the time 15 minutes is enough. So if it's hold for 15 minutes, so it's okay, we can continue drilling to the maximum expected mud weight that we will use. And then this is FIT, just we are start drilling, say for example with 10 BPG, but we know that at the end of drilling or while drilling, we will increase to 12 BPG. So we test the shoe point, this 12 BPG will be okay, or we will lose mud or fracture the formation. This is the importance of FIT. And FIT is done for all section by section. LOT, most of the time, only done in the exploration wells. And if you are already doing LOT before, so just you do FIT and that's it. There is a question, what's the differential pressure? Differential pressure is expression used in the directional work. That is the difference between the on bottom and the off bottom pressures. You know, when you are on bottom and you are circulating, there is a pressure reduction through the formation itself, through the pit, through everything. When you go off bottom and you circulate, you will have a less pressure. So this differential pressure usually determined by the directional driller, and it is a factor of the directional work. This is the difference between the on bottom and the off bottom pressures. How can I calculate the annual pressure loss? This is calculated by the BWD tool or by the hydraulic software that we will talk briefly in the next slide. Okay, so before starting at the practical rig hydraulics is a very advanced topic. So why I choose to put it in this crash course? The 4x4 course is very crash course. You know, you cannot take a lot about the mud in 4 sessions or 4 hours. But just because I know most of the crash courses will not talk about the practical rig hydraulics, so I want to add a value to our course talking about rig hydraulics. Just very quickly, I'm trying to make it quickly, simply. Don't be intimidated by the equation, because all the calculation now is done by software. I just want you to understand how we are dealing with the rig hydraulics. That's it. It's very simple. Don't be intimidated by the equation. Most of the time, for myself, I'm now like 10 or 11 years drilling fluid engineer. I did this calculation only once in my life. The calculation of rig hydraulics. This was like 10 years ago in the mud school. Now everything is done by the software, and even I don't remember this equation because it is complex equation. I removed a lot from this session, from this presentation, because it is not relevant to our scope. Just I will scratch the surface about the rig hydraulics. So let's see the root of our circulating system. This is our mud dump. This is our, okay guys, please stop questions now and we will take questions later. This is our mud dump, and we start pumping the mud inside the stand pipe. The stand pipe is the pipe connected from the rig floor to the mud pump. And this, try to follow with me the path of the mud from the mud pump back to the mud pump again. So the mud go from the mud pump to stand pipe, then to the rotary hose, then to the swivel, which is connect the rotary hose with the drill string, then the killie, and now there is no killie. Most of the drilling is done by the top driver. Then go to inside the drill string, the drill pipe here, then the drill collar, then through the bit, out from the bit to the annulus, come from the annulus to the flow line. This is the flow line. The mud come to the shell shakers to remove the solids from the mud. Go down here, the mud bit, and this is most of the time sand trap, settling tanks, degasser, desilter, mud cleaner, and then come to the suction tank, which is chemical tank. We mix our chemical here, and then go again to the mud pump. So this is the full way of the mud from the mud tank through mud pump, stand pipe, rotary hose, swivel, killie or top drive, the drill string, drill pipe, drill cooler, then the bit itself, annulus, flow line, shell shaker for cleaning, and then back again to the tanks. And for sure, these solids is gathered in the waste bin. So what is the importance of this while you are talking about the rig hydraulics? We pump the mud with pumping pressure, and we receive the mud as a service very calm. The mud comes to the surface without high pressure for sure, because if we have high pressure mud on the surface, it will be lost on shaker. So we optimize our pumping pressure so that it go all this way and come back to us with almost zero pressure or minimum pressure. So we have to ask ourselves where this pressure go away, and this is the main focus of the rig hydraulics. The pressure of the mud is lost all the way from the service equipment, from the drill string, the bit, the annulus, back again to the shell shaker. This is the scope of the rig hydraulics calculation. So we have here 5 pressures. We summarize the pressure loss in 5 pressures. The pressure that lost as a service equipment, which are the standby, rotary hose, swivel, Kelly, all of this is the service equipment. And there is a pressure lost in the drill string itself. The drill string is drill pipe and drill cooler, and there is a pressure lost in the bit itself, and there is a pressure loss inside the annulus. And you have 2 sections of the annulus. The small section, which is around the drill collar, and a big section which is around the drill string. So you are losing mud pressure all this way, from up, down, up again. So the hydraulics, the rig hydraulics scope or objective to calculate all of this pressure. So if we talk about the service connection losses, these losses depend on the dimensions and geometries of service connection. And we have 4 types of service connection. You will find this case 1, the standby, hose, swivel, Kelly, and you will find different sizes. For example, the standby 40 feet long, 3-inch diameter, 40 feet long, 3.5-inch ID, 45. So you will find a different type of service equipment. And for everyone, you have a certain pressure loss. So you are not calculating this one. Most of the software you will have, you will just select the type of the service equipment, and it will give you the pressure loss. The equation of the pressure loss is here, but as I told you, don't be afraid about it. Just this pressure loss is a function of the mud weight, the volume rate, the gallon per minute, the flow rate, as we talk about, and the E, which is the constant depending on the service equipment. This one, the value of E, and the plastic viscosity. That's it. I don't want you to focus on the equation. Just to know that the pressure loss is a function of these factors. And you can easily calculate it by knowing the service connection type, and you will get it. Don't worry. So this is number 1, the surface pressure loss. You have a similar equation to calculate the pressure loss inside the drill string and the drill collar, around the drill string in the annulus, around the drill collar. I remove all of this equation because, as I told you, it is not the scope. Just, I want you to understand that calculating the rig hydraulics is knowing how we lost or where we lost this pressure. Okay, so the magnitude of pressure B2, B3, B4, B5, which is from this chart, B2, B3, B4, B5, it will depend on dimension of drill pipe or drill collar, the mud rheology, mud viscosity, and the type of flow. So you will have different pressure loss if you have different mud rheology, different flow, laminar or turbulent, and we will talk about it soon. You will have different pressure loss at the annulus and inside the drill string itself. So in the industry, we have models. In the industry, we have 3 models for this calculation: Bingham plastic model, Power Law model, and the Herschel-Balkley model. If you are going to work as a mud engineer, especially in the multinational companies like Halliburton and Schlumberger, you will find them all the time using the Herschel-Balkley model because this is the most accurate one. Don't be panicked also about these models and understanding them 100%. You will not understand them 100%. Just get this info that we have 3 models of calculating the pressure losses, which is the Bingham plastic model, Power Law model, Herschel-Balkley model. And I will talk about the difference between them briefly from this chart. We will back again to this. This one. So we have something called Newtonian fluid. We have 2 types of fluid: Newtonian fluid and non-Newtonian fluid. The Newtonian fluid is that when you apply a shear stress, you will have a shear rate and it is not temperature dependent. When you apply a shear stress, you will have a shear rate and it is not temperature dependent. So the Newtonian fluid will start from 0 and it is linear equation like this. There is no effect of temperature, and this is not the case. Our typical drilling fluid is non-Newtonian fluid. Example of non-Newtonian fluid is the toothpaste. The Newtonian fluid, the diesel, the water, the glycerin, the clear prime. But most of the time, non-Newtonian fluid is affected by the temperature. And this temperature and the pressure condition affect the shear stress and shear rate. So our 3 models are here: the Power Law model, the Bingham plastic model, and this is the typical drilling fluid, which is the Herschel-Balkley model. Just, I will give you a quick info to understand the difference between the different models and why one model is more accurate than another one. Try to imagine with me now that you have a droplet or a big volume of honey above your table, and you have a ruler and you are trying to move this honey droplet from the table very gently. When you start moving with small power, the honey droplet will start moving exactly at the same time. This will not happen. You will continue pushing the honey droplet until a certain power, until the honey droplet overcome the friction of the table, and then it will start moving. So you have this stress, shear stress. You are applying shear stress, shear stress, shear stress. Nothing is going down. There is no movement. There is no shear rate. At certain point, when your shear stress overcome the resistance inside the fluid, so you will have a shear rate. And this is our case. This is our actual case in the field. You have a mud. This mud have gel strength, as we talked yesterday. You will apply pressure, and the mud is still trying to crack the friction inside. And once this friction close or break, you will start having a shear rate. This is why there is different models. The power law model, yeah, it is not non-Newtonian. It will affect by temperature and the pressure, but it is not accurate. That's why most of the company didn't use it so far. But the Bingham plastic model and the Herschel-Balkley model, this is the most common because they are considering the point of we have zero shear rate while we have shear stress. And this is the concept of tau zero. When we look at this equation, we have this tau in the Herschel-Balkley model, tau zero. Tau zero is the fluid yield stress when there is zero shear rate. This one. This one. So I feel if anyone don't read before about these models and this hydraulics, I'm sure that you are confused now. I told you it is a big topic, advanced topic. So we will summarize what I want from you to understand. So the most important concept I want you to digest today is the hydraulics is concerned about calculation of the pressure loss from the mud pump back again to mud pump or back again to mud tank. We have surface pressure loss. We have pressure loss inside the drill string. We have pressure loss across the bed itself. We have a pressure loss in the annulus. The pressure loss of the surface we talk about, it's okay. We have the types of the surface equipment that we have, and we can calculate it easily. But we have a models to calculate the pressure loss of this mud inside the drill string and at the annulus. And we have mainly three models: the power law model, the Herschel-Balkley model, and the Bingham plastic model. What is the difference between these models? Just to try to remember the tau zero. The tau zero is the value of shear stress that is applied while we still have zero shear rate. and try to imagine the example of honey droplet above your table. You are trying to push it, but it will not be moved until you're pushing your shear stress overcome the internal friction of this honey droplet. So, because I was intending to provide this presentation to you, so I didn't remove everything. I keep some concepts for you to revise, like what is the meaning of shear stress, shear rate, the viscosity is very simple, the effective viscosity, and yield point, yield stress, elastic viscosity, and friction factor. We talk about the yield strength, and we will talk now about the Reynolds number. You know, we have 2 types or 3 types of flow regime. We have laminar flow, and we have turbulent flow, and we have transitional flow. The laminar flow, when the Reynolds number is less than 2300, and turbulent flow above 4000, and transitional flow in between. What is the important point that you should understand here? The turbulent flow and laminar flow is affected by many things. Affected by the flow rate that you are pumping, affected by the diameter of the string that you are pumping in. So, for example, if we have the same flow rate, and we look at this one, we will have at this area a laminar flow, and we will have in this area a turbulent flow. Why? Because this diameter is small. So this laminar flow and turbulent flow affects our whole cleaning. You remember yesterday when we talked about the cleaning in the horizontal section, I told you that we pump low vis bell, and this low vis bell make agitation, and this agitation make turbulent flow. Then we can clean the hole with the high weight bell. So we should know which part of the well have laminar flow and turbulent flow, and this is important to expect the whole cleaning. And this also is a part of the calculation. When you have turbulent flow, you will have a different pressure loss. When you have laminar flow, you will have a different pressure loss. So you see at this diagram, we have laminar flow. The flow is laminar, smooth. Here is turbulent flow, and sometimes you need both. You need laminar flow in some area and turbulent flow in another area. One may think about it. So why we can switch between the turbulent flow and laminar flow? The turbulent flow producing more friction, and more friction is more ECD. So maybe sometimes we need to reduce our flow rate to avoid the turbulent flow, to reduce the ECD. Sometimes you need the turbulent flow when you need to make agitation for the low side of the well. Okay. So the 3 logical model, as we talk about, Bingham plastic model, Power law model, and Herschel-Valkyrie model. And this is a very simple equation I just keep for you to revise when I give you the presentation. But as I told you, this is not the scope of the hydraulic lesson. I just keep it for you, and I deleted a lot because there is equation to calculate the pressure loss in the drain string, the P2, P3, P4, P5. And the last thing I will talk about before conclusion this one is the optimization of the pressure loss at the bed. We talk about every part, but we didn't talk about the bed itself. The losses happened in the bed here is the most important one. And there is a big topic in the hydraulic called the hydraulic bed optimization. We are designing our bed and our nozzles to have a pressure loss around 65% across the bed itself to provide us hydraulic horsepower, to provide us jetting action, to provide us the required jetting to clean the hole. And this is controlled by the nozzle size selection. And as you know, and as you see, it is a very big topic. I'm just trying to scratch the surface. If you would like to read more about it, try to read it carefully, but try to expect that you will face a serious focused topic, not a simple topic. So I hope this somehow clear, and the message that I want to deliver to you about the hydraulic project or hydraulic topic to deliver easily and simply as I'm trying to deliver it to you. So this is the conclusion of this part. I will keep the presentation for you, for revision, for reading, and I urge you to read more about this if you want to understand it sooner, because if you understand hydraulics very well, you will be a better engineer, as I told you in the start. So that's the conclusion of our presentation for today. And now it's your time for Q&A.
The title of the session was all about pressure, right? But mud engineering, I think it also handle other than pressure. Like, for example, when the wireline logging company need to do some kind of pressure test when they need to set the packer and so forth, the mud engineer usually spot sodium bromide or some kind of chemical across the zone that will be used as a packer setting location to maintain the integrity of that section during a very long test, which could be lasting days. The packer will be set there. So I think the engineering of the mud, the chemical that we use as a drilling fluid, is also covering more beyond just the pressure itself, but it's also the reaction with the formation and keeping the integrity of it. That's just an opinion for me.
Yeah, you are 100%. You are right. I'm not the title of the presentation of today. I don't mean that it is all about pressure. I don't mean all the mud engineering is all about pressure. But I mean our industry or our work, it's all about pressure. When I'm talking about this, because if you lose your pressure control on the well, so you will lose everything. And even as I introduce myself, I am an instructor for the well control, Adam Safe and Well Sharp. And the first thing that we talk about, if we lose the primary well control, which is come from the mud weight, so we are using the secondary well control, which is the BOB, only until we regain the primary control with the kill mud. So it's come back again to mud. So I'm just trying to focus on the great importance of the pressure and the pressure control. It's all about pressure. I'm not meaning that our mud engineering is all about pressure. I told you yesterday is that our mud engineering is a lot to do. We are trying to minimize formation damage, provide borehole stability, shell inhibition, a lot of things, you know, corrosion inhibition. We are adding a lot of chemicals, mixing a lot of different types of mud, different type of treatment. We have a lot of contamination, a lot of things. But all of this will not be done until you are controlling your well. So just I choose the topic name. It's all about pressure to emphasize the high importance of the pressure and the pressure control. I hope I answered your question.
Hello, sir.
So,
Hello, sir.
yes, hello.
Hello, sir. Assalamu alaikum.
Hi.
Very, very interesting lecture today. Believe me, because of this hydraulic course, I have enrolled. And
Please increase your voice. I can't hear you.
I say that, sir, it's very interesting and nice lecture of today because it covers the basic for the junior mud engineer or the trainee. It was very good lecture. If it's possible, can you share the notes with me and with the team? Sir, I have two questions. Can you hear me?
Yeah, but your voice is not 100% clear. So I'm trying here.
It's now clear?
Yeah, try to increase it. Okay, it's good.
Okay. Sir, as we told, there are two types of flow. Sir, so I was assuming that in a drill string, we have laminar flow. And when it came out to the nozzle of the pit, it came into turbulent flow for the whole cleaning and for the cleaning purpose. And when throughout the annulus, it will be still remain the turbulent flow, or at the annulus, it will be again changed to turbulent flow.
Okay, very good question. You know, as I told you, most of the hydraulic calculation is done by software, and I have the privilege to test this when we have a laminar and turbulent flow across the well bore. So most of the time, we have the turbulent flow at the bed area, the nozzle area, and in the narrow annulus around the BHA, drill collar, and stabilizer, and it turned to a laminar flow again once we go to the higher, the bigger section around the drill string, the 5-inch drill pipe or 5.5-inch drill pipe. So you are trying to have this turbulent flow around you know, the source of the cutting, and once you reach it to the bigger section, you are counting on your annular velocity plus your viscosity to hold this cutting until you reach it to the surface. Because as I told you, every parameter of your mud is controlled by a limit, lower limit and the higher limit. For example, you can, when I told you your optimum YB in the 8.5 inch section is around 16 or 15 YB. So you will tell me, okay, so why not increase it to 20 or 25 YB? You will have a better hole cleaning. But I will remind you that if you increase the yield point, if you increase the viscosity too much, you will have too much friction. You will have too much annular pressure loss. You will have higher ECD. So you are controlled by a lot of parameters. You are trying to balance everything. You cannot increase the viscosity too much to provide hole cleaning and risk with the ECD. You cannot increase the annular velocity too much and risk with the ECD. You understand the point?
Yes, yes, I understand. Means, sir, in narrow diameter, we have turbulent flow, and when we go to the upper section, we have laminar flow.
Yes, that's correct.
Yes, I understand. I understand.
Yeah,
And
that's
sir,
correct.
one more. What are the pressure losses around the bit and drill string? Can you analyze, because when the flow come out from the flow line, we have very less pressure loss. So do you have some diagram that explains the pressure loss along the different parts?
Okay. As I told you, for example, if we pump with the standby pressure or the pump pressure is 3000 psi.
Yes.
If we put a pressure gauge in the flow line to measure the pressure of the returning mud, it will be almost nothing. It will be like 1 or 2, because if we receive more pressure than this, we will have overflow on shakers. So we lost all the 3000 psi or most of it through the journey of the mud from the mud pump back to the flow line. 65% of this pressure is designed to be lost around the bit and the bit nozzles to provide us with the horsepower and the jetting action. So I will try to open to you one of my reports. Just I cannot do this, sorry. Okay, so just try to understand it now, or just to have this info. We have some parameters related to the bit itself, which is the hydraulic horsepower per square inch, the jetting action, the horsepower itself. All of this is dependent on the pressure loss and around the bit. And this is done by the nozzle selection. And there is something called the TFA, the total flow area. The TFA is the combination of the flow area of the nozzles. For example, if you have 10 nozzles and each one it's 13/32 inch, because the nozzle size is very small, we calculate it as a fraction of 32. So when I told you it is 13/32, so it is when I told you 10 nozzle 13, so this 13 is over 32. So this nozzle selection made a lot in the calculation of the hydraulic horsepower and jetting action, which affect the whole cleaning. That's why we designed the hydraulic of the mud so that 65% of the pressure of the mud lost around the bit only. 65%, a lot. And the remaining will be lost in the annulus, as we talk about, the annular pressure loss, and inside the release string in the service, but 65% or even 70% around the pit. And this is by design. It's not like this. Okay, there is a question here. It's clear for you?
Yes, sir. Yes.
Okay. What is the cut term used for? Okay. The mud cut, usually when we have a gas well drilling, but a lot of gas, not just background gas. So, for example, we are drilling with 9 ppg, and when we are measuring the mud weight, we found the mud coming out is 9.8 or 9.9. So we have 0.1 or 0.2 mud cut or gas cut or mud cut due to gases. Okay. Also, we can use this term while we are reducing the mud weight. Company man asked me, please cut the mud weight to certain value, but this is not common to be used in this situation. We're using it commonly when we have a gas cut mud. Have to head work now. Okay, sent. Okay, bye, Alberto. A lot of my confusion has been clear, especially about. Thank you for this, Mohsin. But as I told you, the time and the topic, this topic need a lot of time. Usually, the rig hydraulics is explained or described at the advanced mud courses. Usually, you know, when I take my mud school and the advanced mud school, I take 2.5 months. 2.5 months of mud school, plus another 1 month advanced mud school, and all of these years of experience. And the rig hydraulics topic may be till now for certain mud engineers who are not reading about it, it's confusing. And because it is not a routine task on the rig. So the rig hydraulics is very important, and try to understand it, try to read more about it. I guarantee if you understand it very well, you will be better engineer and you will understand a lot about your mud and about your pressures. And you will get appreciation one day about this, believe me. Okay, there is another question here. How to access the bore pressure having only seismic or logs data? Most of the time, we this is not provided to us as a service companies. This is to the operating company that they have the seismic or the logging data or even the wire logging. So as a mud engineer, I'm just dealing with what I got from them, but I know how they got it. They got it with most of the time wireline logging, and also the BWD, the pressure wire drilling. We can calculate this bore pressure. If there is 100% gas, terminology used for what in oil field? I can't get this question. What do you mean, Abdul Hafiz?
Hello?
Yes. What do you mean about this question?
Yeah. Like you see the mud, sometimes company man says the proportion of the gas get increased in the while churning the gas, what do you call this, degasser. It shows the proportion of the gas is very high, like it is up to 100%. In that means we are not getting mud exactly, but we are getting gas in that column in the degasser. So means it is the example of kick that means we are losing our mud and we are getting a gas instead of the mud. Like that condition I wanted to ask. Like sometimes they use the 100%, we are getting gas coming from the reservoir this way.
Okay, but 100% gas is you are not you have a gas kick, and when you have a gas kick, you will not wait until you have a gas in the service. If you have a gas service, so you have a blowout, not even a kick. When you have a gas kick, you will have, okay, close your mic, please. If you have a gas kick, so you will notice, the driller will notice a pressure variance, and he will notice that we have a kick, and he will close the well. And once he closes the well and calculates the difference between the shot and drill pipe, shot and casing pressure, and all of this stuff, so he knows that we have a certain amount of gas, say for example 5 barrel, 10 barrel, and we start to make our calculation to kill the well. And while killing the well, whatever the method you are using, weight and weight or driller method, so at some time you will have this gas out as a choke, and you are controlling it by passing this mud to the mud gas separator and then to the flare line. So you will never ever see 100% gas, 100% gas on the surface in your logging tool. This is a crazy. You will have a kick at this time. You will have a blowout, not a kick. So the mud logger calculate, or the tools of the mud logger calculate the gases, the background gases and the gases at the well. And maybe, yeah, you are right, it will increase, but it will never go to 100%. You will never have your well 100% of gas. This is not the situation. At this time, you will be already evacuated from the rig, and the rig is in burn. Okay, so this is not terminology used in the oil field. Rafael, thank you for the lecture. Thank you, brother. Today, must say it was very impactful. Thank you. Say, please tell us about CCI. What is the relation with cutting life lifting? What do you mean CCI, Bana?
Hello.
Yes, what do you
Hello.
mean? Yes, yes.
Cutting carrying index. CCI.
Cutting carrying
Cutting carrying index.
Okay, I will. You mean this one?
Hello.
I write it in
Yes,
the
sir.
chat. You mean this one, cutting carrying index?
Yes, 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 sir.
Yeah, it is not a common expression used in the oil field. It's just, you know, the yield point. When we define the yield point, we define the yield point as the cutting, the ability of the mud to cutting or cutting carrying to the surface. Okay, so this cutting carrying index is related most of the time to the yield point, because in the whole cleaning and the viscosity itself, the rheology and the viscosity is a big topic. You have the plastic viscosity, you have the funnel viscosity, yield point, low shear yield point, you have the tau zero, you have a lot. So, and when you are drilling vertical, deviated, horizontal, the viscosity that performs the whole cleaning become different. So just the cutting carrying index, it is related to the yield point most of the time, and also related to something called the sextropic effect. Sextropic effect is that you are designing your mud to not only carry the cutting to the surface, but the mud should discard this cutting on the surface by the shell shakers. Maybe sometimes you have a high viscosity that is making a high surface tension between the mud and the cutting, and the removal of the cutting itself is difficult from the surface equipment. So this is not good thing to design. So the cutting carrying index, as I told you, it is not a common, but it's just related to the yield point and how we are cleaning our mud. Okay, what else we have? Okay, looks like we are done with questions. Thank you guys for this, for listening today. And I hope the topic of hydraulics not increase your confusion. As I told you, it was very easy for me to ignore this topic, but I see that it is an added value. I need to deliver it to you. Maybe you will remember this 4x4 training with this topic itself, because most of the model engineering topic try to avoid this confusing topic, but I intentionally want to try to scratch the surface with you about it to help you. If any one of you want to dive deeper, he will be very happy to understand this interesting topic. So thank you all, and inshallah we will meet you tomorrow at the same time with a very interesting lecture. It will be like you are with me on the rig, and I will ask you to participate with me. I will give you a mixing recipe, and you will propose how we will mix these chemicals. And through the discussion, I will show you the difference between the mud cooker and the mud engineer. So stay tuned, prepare yourself. I need every one of you to have a paper and pen tomorrow, inshallah, and be ready for participation. See you soon, inshallah, and have a nice day or night. Assalamu alaikum wa rahmatullahi wa barakatuh. And I will share the presentation with you.
Thank you so much, Engineer Ram. Thank you all.
Thank you. Assalamu alaikum wa rahmatullahi wa barakatuh.